Hey there, my name is Alejandro and welcome back for day 13 of me doing the Daily LeetCode challenge until I reach 1 year's worth of green contributions here on GitHub. So today's problem is for July 29th and 2024. And if you have not noticed already, you'll see that I've already actually solved today's LeetCode problem. So as a quick context for what happened is I ended up recording my video as usual, like every day on QuickTime. And here I can minimize my little self-recorder here, but and it took me a good 2 hours and 46 minutes chunk where I was just kind of here like struggling through the problem with my own way, trying to figure out how to do it, blah blah blah, etc etc etc. It ends up going to a dark screen mode here. I'm just trying to debug. You can see in like the bottom right, I'm just trying to debug stuff going on, blah 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 blah. I end up trying to look at a solution because I got too stuck after 2.5 hours of trying. I end up realizing the little foresight that I had made at the beginning and ended up publishing my own solution and saying goodbye to you guys. So unfortunately what happened is I ran out of disk space, and in clearing disk space I actually accidentally deleted the very file that I used to record this video. And I tried everything. I tried Time Machine, I tried disk drill, I tried many ways of recovering this file. One option would be to video record this file and so on, but I know the quality would be a lot lesser, and you probably hear me snore while I sleep and so on, which would be no good. So I've just decided to kind of re-record the problem. I mean, this will be a kind of an unfair advantage because now I understand how to solve it and so on. Here's already a quick sneak peek of the solution that I presented. So yeah, I'll go into the problem. The problem's name is problem 1395, count number of teams. Essentially, I'll just read the description very quickly. There are n soldiers standing in a line. Each soldier is assigned to a unique rating value. You have to form a team of 3 soldiers amongst them under the following rules. Choose 3 soldiers with index I, J, and K, with rating I, rating J, and rating K. A team is valid if rating I is less than rating J, and which is less than rating K, or rating I is greater than rating J, greater than rating K, where 0 less than or equal to I, less than J, less than K, less than N. Return the number of teams you can form given the conditions. Soldiers can be part of multiple teams. So here, I'll kind of restart the problem, and I'll just kind of explain how to solve the problem efficiently, like how I did in the end. So essentially, the trick to this problem is, well, first of all, you want to count the number of permutations of ijk that exist for this problem, because that's the thing that you're trying to return. And a valid permutation of ijk is such that the indices I, J, and K are in increasing order like this, and it happens to be that their corresponding rating values in this array rating that we're given when indexed at those indices I, J, K happen to either be in increasing order or inside of decreasing order, right? And so the very first thing that you should realize is, hey, in this problem, we kind of want the order of these two conditions. How about we first solve this problem, right? We find every single valid permutation of I, J, K that satisfies this criteria, and then once we have the number of those, count the number of IJK permutations that satisfy this criteria, and then add those two numbers together, right? So essentially, when you solve one subproblem, you kind of get the other subproblem for free because you just change the direction of the sorting and so on. So and the idea is, right, like, since these are pretty much almost the same problem, let's say it doesn't matter which what asymptotic time complexity this takes. Let's say it's O of n, then or O of n squared, I think will be in this case. Then it's okay if you run an O of n squared algorithm again, because 2n squared is basically O of n squared anyway. So let's just get straight into that. The very first problem that we'll solve is for this subcondition. So what we'll do is say, hey, we notice that these triplet pairs, we need an index to be in the middle, this J index, right? So we can specify a specific J index and count the number of IJK permutations with that fixed J that exists inside of this rating array. And in fact, we can do this for every single valid rating of J. So the idea is that we're going to create a result value of 0, which is what we're going to return in the end. And then we realize that, first of all, okay, J must be greater than I, which is greater or equal to 0. So it must be greater than 0, so it must range from, at minimum, 1 all the way up to some value less than k, which is less than n, which means that since k is less than n, it's at most n minus 1. Since j is less than k, it must be at most n minus 2. And of course, the second parameter in range doesn't include the actual number you fit in. So to make sure that n minus 2 is the greatest value that j can be, we say for j in range 1 to n minus 1, right? And again, j must be greater than I, which is greater or equal to 0. So at minimum, its value can be 1. So this is all the possible values of j that exist. And for each of these fixed values of j, right, we're going to compute, okay, how many I, j, k permutations exist with this specific criteria met, right? And of course, when we do this for every single possible value of j, or index j, then we get the total amount of I, j, k permutations that satisfy this criteria, right? And the way we're going to do this is say, hey, now that we have some fixed j, it doesn't matter what it is, it doesn't matter if it's 1, it doesn't matter if it's n minus 2, it doesn't matter if it's n divided by 2, like we have some fixed j, and we're going to, again, iterate this for every single possible value of j. But now that we have this fixed j, we're going to say, hey, we want to find these I, j, k permutations, right? So first, we know that I must be less than j, and then that rating of I must be less than rating of j. So how about we count the number of elements that occur before index j in rating and whose value is less than rating of j, right? So let's do that. Let's call this num before, the number of elements before j. So we want to find elements in rating such that one element occurs before j in the array, jth element in the array in rating. 2, rating value of that element is less than rating of j, is smaller than rating of j, right? So we're going to loop for every single element that happens before j, which is going to be for I in range. Remember these I indices that are less than j, so minimum value is 0, all the way up to j itself, but not including j. So for I in range j, we're going to say, okay, this is only indices that happen before j, and if rating of I is less than rating of j, then this is a valid number that we can consider. So we're going to say num before is going to be plus or equal to 1. And then we're going to do the very same thing, but with these k values, right? These k values, they must appear after j, and their rating associated value must be greater than that of j's. So we're going to say, okay, num after, similarly, we're going to say is equal to 0. We want to find elements in rating such that, again, 1 element occurs after j element j in rating, or yeah, jth element in rating, and 2, rating value of that element is greater than rating j, right? So we're going to say for k in range from the element after j, so j plus 1, all the way up to n, that if rating of j is smaller than rating of k, right, from here, and then we say, okay, num after plus or equal to 1. And now the trick that you have to realize is, let's do a quick example. Let's say, for example, that we find 2 elements before j, I1 and I2, and whose rating such that rating of I1 and rating of I2 happen to be less than rating of j, and also 3 elements, k1, k2, and k3, such that rating of k1, rating of k2, rating of k3 all happen to be greater than rating of j, right? Then what we can say is like, okay, how many permutations exist for this specific j, right? Well, we say, okay, there's one here, I1, comma j, comma k1 here, right? Because it's like, we know that I1, again, these I1s and I2s and so on are the ones that we found here that we know are indices smaller than j. These k1, 2, 3s are from here that we know are indices greater than j. And then we know that, like, okay, the rating value of these indices happen to be less than j, and then j happens to be less than the k indices over here in terms of their rating value. So we know that this is a valid permutation, right? so I1, j, and k2. And then we know that I1, j, and k2 is a valid permutation, the second valid permutation. Third, we have I1, j, and k3. And what you're going to notice is that for this first I1, we're going to map it. There's going to be a valid permutation that exists with every single one of these elements here. And then similarly, now that we're done with these, we're going to do the same thing for I2. So we're going to see the fourth permutation is I2, comma j, comma k1. And then similarly, 5 is I2, comma j, comma k2. And then number 6 is going to be I2, comma j, comma k3. So what you're going to see is that since j is fixed, the number of total ijk permutations that exist for that fixed j is going to be the number of quote-unquote valid elements that we found that occurred before j in the rating array at times the number of elements that are valid that we found after j in the ratings array, right? Because it's like for each of these, where there's going to exist a permutation which each of the elements in here, and specifically this j value is not going to change, so it doesn't affect the result. The point is that we're going to do it for every valid index of j. And so essentially, like, where does the sixth number come from? Well, 6 is equal to 2 times 3, which just happens to be the length of this array that we created here and the length of this array that we created here. And these values really represent this number 4 and num after value, right? Num after is the number of these k1, k2, k3, etc. elements that we found that happen after j and whose rating is greater than that of the jth element. And similarly for these indices I, like I1 and I2, this number 4 value represents the number of those that we found, such that their rating happens to be that of j's. So what we're going to do is, hey, to this res variable that we created at the beginning, we're going to add to it the product between number 4 and num after, right? And then that way, when we do it for every single valid index of j, we're going to get every single the count of every single valid ijk pair that matches this exact criteria and this exact criteria right over here. What you're going to notice is that if we do run this, however, here I should I should return res, and actually there we go. I can probably get rid of this example. Whoops. That was just for explanation purposes. But if we run this, we're actually going to get an undercount, or perhaps an exact count. Yeah, so sorry, n is equal to length of rating over here. So for these ones, we actually get a perfect solution, but for case 1, we actually get an undercount. Now, the reason why is that we've only been considering this condition over here. Remember, the valid ijk pairs are one that matches this criteria, or this one with those increasing order of indices. So what we can do is say, okay, this is when the rating values are sorted in increasing order. This is when the rating values are sorted in decreasing order. So we can rename this number 4 to be number 4 increasing, number 4 increasing, and then num after increasing, num after increasing, and then we have number 4 increasing, num after increasing. But now we can also introduce a new variable, which is num before decreasing, right? Or num after decreasing. And the idea here is that we're also going to count the number of elements that happen before j whose rating value is greater than that of j's, and then the number of elements that happen after j whose rating value happens to be less than that of j. So here is just a very simple addition of logic. It's like if rating of I is actually greater than that of rating j, as in this condition right over here, then we're going to do num before decreasing is plus or equal to 1. And then if here rating of j happens to be greater than that of rating of k, then we're going to do num after decreasing is going to be plus or equal to 1, right? And here at the very end, we're also going to add to res not only the valid ijk, the count of valid ijk permutations that happen to satisfy this and this criteria, but the ones that also happen to satisfy this criteria as well as this condition, right? So num before decreasing times num after decreasing. And then now when we run this result, we'll see that we actually get the correct answer. And if we submit this, it should again be the correct answer, right? And so it works nicely that way. I'll just quickly remove these comments right here. but is this the only place I use n? Likely so, right? Whoops. Where do I use n? Okay, it's okay. I'm just gonna say n equals, yeah, let's just keep it how n equals length of rating, and we're gonna say n minus 1 over here, get rid of that, and submit again. 40%, maybe if we run a couple times we'll get a faster solution, but otherwise that's kind of the idea, right? Maybe if we transform these into elifs, I mean it really should make a difference, but yeah, that's kind of the solution. So hopefully that makes sense. This was not a little clever solution that I had thought of myself at the beginning. I did end up like struggling, you know, for 2.5 hours before I was very stuck on this specific idea that wasn't going in a very good direction, and I did end up going through a solution, reading through the code, and kind of understanding the intuition behind it. What I did realize during my 2.5 hours is that I knew there was going to be some kind of trick with how do you call it? Like kind of like in two-sum, where it's like the typical brute force solution would be O of n squared, but then you can apply a little trick to kind of decrement that from O of n squared to O of n. Like here the brute force solution was O of n cubed, and this clever solution brings it down to O of n squared, because here if you try the brute force solution, you know, for I in range n, for j in range I plus 1 comma n, for k in range j plus 1 all the way to n. And in fact this is only up to n minus 2, and this is only up to n minus 1. And then it's like here you have a count variable is equal to 0, and then you say if the OR of these two, then count plus or equal 1, and then just return count. You'll notice that like for these this is absolutely correct, right? And whoops, again, n equals length of rating. So for this is absolutely correct, but of course if you try running it you're going to realize that it is much too slow asymptotically. And so my whole goal throughout my solution was try to figure out like, okay, we have this obvious brute force n to the p type polynomial solution. Let's kind of apply the same logic in two-sum, where you kind of do something clever in two-sum with the case of a hash set to bring down the complexity from n to the p to n to the p minus 1. And this was kind of the trick, where it's like you realize that like, hey, for any fixed j, if you take the number of valid elements before and after and then multiply those two numbers together, that is quote unquote the number of valid permutations that exist for that specific index j, and then just iterate that for every single index j that you have, and there you go, boom shakalaka, you got your solution right there. And so yeah, so of course I'll just remove this little condition. This is just the solution. So I hope that made sense. Maybe this video is actually a little bit more useful in the sense that it's more of like a here's a solution to this problem instead of me struggling. Otherwise, if you were looking forward to having a video of mine where you struggle alongside me, I'm very sorry. I tried absolutely everything to try to get this recording working. At least though, maybe you'll appreciate the fact that this video is closer to 20-25 minutes than 2 hours and 45 minutes. But yeah, otherwise, thank you so much for watching. If you do want to do the same thing that I do, the extension that I use is called LeetSync. Essentially what they do is they take a direct solution that I submit on LeetCode that happens to be accepted and publish it directly to my GitHub. I trust this extension, but by no means do you have to trust this extension yourself. But to show a quick demo of what it does, this problem was called what? Count number of teams. If I come into my GitHub, into my LeetCode repository, and I control F for count number of teams, and you'll see 3 minutes ago there was a solution. You'll see that I uploaded the readme an hour ago because that's when I recorded the solution for the very first time and got my first working solution. But otherwise this 3 minutes ago is just the me submitting my last solution all the way up on GitHub that we just covered in this video. And yeah, that's pretty much it. This this extension is just very, very convenient if you end up wanting to do something similar to what I do. But otherwise, thank you so much for watching. If you happen to have any feedback, please make sure to leave a comment. It would mean the world to me, and I'll make sure that I reply to every single one that you have and take any feedback that you have to heart. Otherwise, if you did like this video or found it useful, if you left a like, that would mean a lot to me. But otherwise, I'll catch you in the next one, and until then, ciao ciao my friend. So thank you so much for watching. Bye bye.